Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at the roots of unity. So in this topic, we will define the roots of unity and see how to find them. The point of this topic is to make sure you understand the previous concepts we have already learned in this course. Now, the second roots of unities are all those numbers which, when squared, equal the value 1. Now, you already know what these are. These are z equals 1 and z equals negative 1. Another way of looking at this is there are exactly two roots to the polynomial z squared minus 1, and z equals 1 and z equals negative 1 are those roots. All right. Let's go on and look at the fourth roots of unity. The fourth roots of unity are all numbers which, raised to the power 4, equal the value 1. Well, we've already seen that as well. This includes 1j, negative 1, and negative j. Each of these raised to the power 4 will equal 1. These are, again, the roots of the polynomial z to the fourth minus 1. You can plug any of these into that polynomial and you will get the value 0. And there are exactly 4 such roots. And because these 4 are unique, these must be all of them. Now, the third roots of unity are all numbers which cubed equal the value 1. Now, this of course includes z equals 1, but what else? Well, first of all, we do realize that these are going to be the roots of the polynomial z cubed minus 1, and there will be exactly 3 such roots. Now, in polar representation, any such root will be of the form 1 phase theta for an appropriate angle. The magnitude must equal 1 because the magnitude of r phase theta raised to the power 3 is r to the 3. The only positive value such that r cubed is equal to 1 is 1, and therefore the magnitude of any third root of unity must be 1. We don't know what theta is, but we do know that 1 phase theta raised to the power 3 is 1 phase 3 theta. Now, we need 3 theta to be equal to some multiple of 2 pi in order to be equal to 1. It can be 1 or 2, doesn't matter. It just has to be a multiple of 2 pi. Consequently, theta must be of the form k times 2 pi over 3, just solving for theta. All right, let's plot these when theta is the form k 2 pi over 3. When k is equal to 0, we get the point 1. When k is equal to 1, we get this point over here, which has phase 2 pi over 3. When we let k is equal to 2, we get this point down there that is equal to 1 phase 4 pi over 3. And finally, if we let k is equal to 3, well, wait a second, that's just 1 phase 2 pi, which is equal to 1 phase 0, which is equal to 1. All right, so as you can guess, if you tried k equals 4, you'd get the next point again. The important point here is there are only 3 roots, cubic third roots of unity, and we have found 3 such values. Consequently, this must be all of them. Notice that the 3 angles separating these 3 complex numbers are all equal. So all 3 of those angles are equal, and all 3 of those angles are equal to 2 pi over 3. Now, the fifth roots of unity are all numbers which, raised to the power 5, equal the value 1. These are the roots of the polynomial z to the 5 minus 1 equals 0. There will be exactly 5 roots. Once again, as before, we'll assume it is of the form 1 phase theta for an unknown theta, and that representation raised to the power 5 is 1 phase 5 theta. We require that 5 theta be a multiple of 2 pi. Consequently, theta is equal to k times 2 pi over 5. And now let us plot these for various values of k. First, when k is equal to 0, we get the point on the complex plane 1. When k is equal to 1, we get this second point where the angle or argument is 2 pi over 5. The next has an argument of 4 pi over 5, then 6 pi over 5, and 8 pi over 5. At this point, we have found 5 such values, and you are already aware that each of these is a root of the polynomial z to the 5 minus 1. Because it is a polynomial of degree 5, it must have exactly 5 roots, and because we have found 5 values that are definitely roots, consequently, this must be all of them. So if we substitute it in the value k equals 5, you will notice that once again, as before, we ended up at the root 1. Notice again also that all of the angles between these various complex numbers are equal, and all of the points again lie on the unit circle. Now, the nth roots of unity, where n is an integer greater than or equal to 1, are all numbers which raised to that power n equal the value 1. So again, these will be the roots of the polynomial z to the n minus 1, and there will be exactly n roots, and as you may guess, there are going to be n distinct roots, and they will all lie on the unit circle. Again, this is because if we require that a complex number 1 phase theta raised to the power n is equal to 1, then 1 phase theta is equal to 1 phase n theta. And we require n theta to be some multiple of 2 pi. So therefore, theta must be k times 2 pi over n. So thus, the roots will have the arguments theta is equal to k 2 pi all over n, where k will run from 0 to n minus 1. Of course, when k is equal to 0, we just have the value 1. When k is equal to 1, we have the point 1 phase 2 pi over n, then 4 pi over n, and so on and so forth. And we can do this for every single value of k up until when k is equal to n minus 1, in which case we have the last and nth root of unity. Again, when k is equal to n, we will simply have the value 1. Okay, and if you notice, the angle between each of these complex numbers in turn is equal. Now, the nth roots of unity are used in something called the discrete Fourier transform, and this involves going from either the time or space domains to the frequency domain. This is a very powerful and useful tool for engineers, especially when we start dealing with a fast Fourier transform, a very, very fast matrix vector multiplication. So, in this topic, you now understand the concept of the roots of unity, you know how to find them, and you've applied numerous ideas with respect to powering the polar representation and the concept of the roots of a polynomial of the form z to the n minus 1, which must have n roots, and we have found that it does indeed have n distinct roots, each with multiplicity 1 that we can find. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!